Okay, we are off to chapter 3 here. We're going to talk about bonding. Next couple of chapters, 3, 4. We'll talk about some bonding. We'll then talk about geometry and all that fun stuff. Then we'll come back to chapter 3, I think, towards the end of that, and we'll talk about nomenclature and naming things. But we're going to talk about bonding in this chapter, and we're going to focus on 2 types of bonding and 2 different types of compounds. One is an ionic compound and a sort of ionic bonding. And when we have an ionic compound, it is much like the name implies, it is about ions, and it's always when metals and non-metals come together. And as we talked about in the previous chapters, based on those sort of periodic trends, we do find that the metals are really the ones that will give away their electrons and become positively charged and cations, and our nonmetals are the guys that will accept those electrons, become negatively charged, and become anions. And remember that when you do have an ionic bond, there's absolutely no sharing of electrons. So that's an important distinction between those. No sharing of electrons, as we'll talk about. We'll also talk about covalent compounds, or sometimes referred to as molecular compounds, and that's usually between 2 nonmetals. And really the difference that occurs, as we'll talk about, when we do get sort of 2 nonmetals together versus a metal and a nonmetal is, again, those sort of periodic trends. So all the nonmetals are pretty much in the same location on the periodic table, which means they have very similar periodic trends in terms of things like ionization energy, electronegativity, electron affinity, which means when 2 nonmetals get together, the best they could agree upon is to actually just share the electrons, because neither one really wants to give away their electrons. So they're both going to go pretty much going to share it. So there is sharing of electrons that occur here. And as we'll talk about, it may be equal or unequal sharing of electrons, but there is some type of sharing that's going on between those 2 nonmetals. And again, that's very different than what we do see with our metals and nonmetals, as they're on sort of opposite sides of the periodic table. So as we talked about, metals are pretty much willing to give away their electrons. Nonmetals are really willing to accept the electrons. So we do get that transfer of electrons that occurs in an ionic compound versus what happens when you got 2 nonmetals that basically want to hang on to their electrons, sort of get together. Now, what helps us sometimes understand bonding, and a very common way that we represent bonding is through Lewis dot symbols. They're sometimes just generically called electron dot symbols. And when atoms come together to interact, it is, again, just the electrons that basically participate in it. And it is those outer electrons. So it's those really valence electrons, like we talked about, I think, in the previous chapter, that are involved in bonding. So the core electrons are not involved in bonding. It is just the valence electrons that we see. And a reminder that the pretty simplest way to figure out valence electrons is, again, it does equal the group number on the periodic table. So everybody in group 1 has 1, 2, obviously 3, 4, 5, 6, 7, and 8. The one exception, as we talked about, I think, yesterday as well, is helium there in group 8. Again, helium only has 2, again, because it only has 2 electrons total, but everybody else there in group 8 will have 8 along the way. So obviously you could also write out the electron configuration like we did and sort of figure it out that way, but again, probably faster and much easier would be just to use the group number. The good news is, as we talked about with transition metals, they don't sort of get to noble gas configurations, a little bit different in terms of how they lose electrons and stuff like that. We really don't do too much with those guys at all in terms of bonding. So you could just basically go straight up with the group number there. So really a Lewis dot symbol is nothing more than the actual symbol for the element, and basically 1 dot to represent each of the valence electrons that are there. There is sort of no main rule other than, again, you kind of use the symbol, and really 1 rule is no more than 2 per side, basically. So a lot of times people will put them on basically 1 at a time and then kind of go back and pair it. but there really is no sort of rule other than you shouldn't put more than 2 per side. And obviously there's 4 sides there to the element symbol, which means the magical number usually in bonding is 8. Yeah, and 8 is sort of what everybody's trying to get to. And as we'll talk about and have talked about last time, that is really the goal of all bonding, both ionic bonding and covalent bonding, is for everybody to achieve the same electron configuration as a noble gas because they're very stable. And 8 obviously puts everybody to the same configuration as those noble gases. So here, as you can see, again, everybody in group 1 has 1, 2, and obviously as you go across there, we have 3. Once again, there's our helium that again only has 2. So 8's a really important number in terms of bonding. That gets everybody to that electron configuration like our noble gases. One also really important thing to remember is our friend hydrogen only needs to get to helium, which means hydrogen should only have 2 electrons. So really important to not do that with hydrogen, put any more than 2. It only needs to go forward basically to helium. So we can use Lewis dot symbols to help us understand the bonding really in those 2 types of compounds. Ionic compounds we talked about at the beginning there, that again is going to be our metal and non-metal. And pretty much you know it's ionic. As soon as you see that combination ever, it's pretty much going to be an ionic compound. And again, our covalent guys, which is our 2 non-metals together. As we talked about in terms of those general trends, things with low ionization energy, they tend to form cations. Again, ionization energy being the energy required to remove an electron from the gas phase. So if it has a low ionization energy, it doesn't take a lot to convince it to let its electron go. And things with high electron affinity again is the energy change that occurs when somebody gains an electron, tend to form anions. Again, electron affinity increases basically in general as you go up and to the right on the periodic table. So these general rules tell us that most likely our cations are going to come from the left there on the periodic table, and our halogens, oxygens, everybody on the non-metal side there is going to be our anions. So let's take a look at an example here, which is lithium fluoride. So if we were to look at lithium, which is right there in group number 1, we would know that lithium here would have 1 valence electron as it is part of group 1. We have fluoride, which is fluorine, and fluorine is group number 7, which means it should have 7 valence electrons in this case. And if we look at the electron configuration for each of these, and a reminder, as we talked about, they do not have charges or anything. So this is 1s2, 2s1, as lithium has 3 electrons. If we look at fluorine, fluorine is 9, which means 1s2, 2s2, 2p5. These here being the 7 valence electrons that we see in the picture. This being right here, obviously the 1 valence electron for our lithium that we see in there. Obviously, as you can see, core electrons are not included in the Lewis dot symbols. It is important to remember, obviously, they still have those electrons, but they are not involved in bonding, so we don't put them into any of the pictures. So in this case, we basically have a metal and a non-metal, so that with all those periodic trends means that pretty much lithium's going to go, you could have my electron, no problem. And it's going to shuttle over there an electron to the fluorine. The result of that is when lithium here will now gain a positive charge as it has lost an electron. The fluorine will pick up that electron. And because it does pick up an electron, it also will gain a charge as well, and it will be negatively charged. Now, typically when we do draw Lewis structures here for ionic compounds like we're drawing here, we always include the charges, and usually you at least put brackets around one of them, like the negative guy or maybe all of them, but you do want to put the charges. That indicates that there's no sharing of electrons here. Again, this being an ionic compound, no sharing of electrons happening in this case. And again, we know this because this is a metal and a non-metal, which means this is ionic. So it is that positive and negative attraction between those two ions that basically is holding it together. That's what's referred to as electrostatic attraction. Opposites attract. Now, what happens in terms of the electron configuration for each of these guys when they do become ions? Well, the lithium here gave away that electron, which means it now only has 2 electrons, which means its electron configuration on the other side there is 1s2. And that is the same as helium's configuration, right? It has the same 2 electrons. The fluorine has room right here in the p subshell, so that is where it's going to stick that electron that is coming in. And when it does so, it ends up with 1s2, 2s2, 2p6, and that is 10 electrons, which is the same as neon. So as what always occurs here in an ionic compound, and really the purpose of the bonding here is they both have now achieved noble gas configuration by, in this case, transferring electrons. Gaining and losing electrons allows both of them to reach that really stable state of the noble gases there in that particular case. Also important, as we talked about last time, when we were talking about electron configuration, they do not become those elements, but they become similar to them in the sense of how many electrons that they house. They are still, obviously, in this case, lithium and fluorine, because they still have the same number of protons, not involved in bonding, just the electrons are involved, and they become like them in terms of their electron configuration. Any questions on that there? I think that's what this should say, pretty much. So that is really the basis of an ionic bond, that electrostatic attraction. And also, as we talked about, the strength of those bonds does increase with the number. So again, if you're kind of putting higher charged ions together, it's going to be held tighter than the negatively charged ions. The other thing that we also talked about when we're talking about electron configuration and ions as well, obviously the cation is going to become smaller than the neutral ion, the neutral atom, because it has lost some electrons, while the negative anion is typically going to become larger than its neutral counterpart as it gains those electrons in its sort of electron field, if you will. So let's take a look at another example. This is calcium oxide. Once again, when I see calcium, I know that is a metal. Oxygen is a non-metal. So really, once again here, that is really all the information that I need to know that this is definitely going to be an ionic bond. We know that we're going to have some transferring electrons because, again, of the opposites or locations on the periodic table. We could start with calcium, which is group number 2, which means calcium here will have 2 valence electrons, being from group number 2, and it is number 20 up there. So you could write the electron configuration as argon 4s2 in this case. And those would obviously be the 2 valence electrons that we see in the picture. We're going to do our oxygen, which is group number 6 on the periodic table there. Do it like that. And its electron configuration, 1s2, 2s2, 2p4 in this case. And this being the 6 valence electrons that we see in oxygen. Again, because of their differences in sort of their periodic trends, we're going to see the calcium being willing to lose its electrons to the oxygen. So we're going to send this guy over. Now, if we laid up right there in terms of just transferring 1 electron, does that do it for the situation for each of those? It really doesn't. It will only move calcium back to like potassium, which is not a noble gas, right? And I'll kind of only move oxygen forward to fluorine, which is also not a noble gas. So in this case, the calcium definitely wants to give away both of those electrons. When it does so, at that point, we will now end up with a calcium that has gained a +2 charge. Again, doesn't have a charge to begin with. And we will end up with an oxygen that will pick up those 2 electrons. And the result of it picking up those 2 electrons means that it will achieve a -2 charge from those 2 electrons that came in. Again, the positive and negative attraction here is what holds that together. Now, if we look at what happens here in our electron configuration, it is these 2 electrons here that is lost by calcium, which means calcium really ends up with 18 electrons, which means it has now been able to move backwards to argon's electron configuration. Those 2 electrons that were transferred over to oxygen will find room right here in the p subshell, as it's got a couple of spots for those 2 electrons, and it will fill up those electrons, 1s2, 2s2, 2p6, and that is 10 electrons, which again is neon's configuration. So once again here, by both transferring electrons and gaining electrons, both of the sort of elements here are able to reach that noble gas configuration and be in a very sort of stable way to do so. Any questions on that there? Again, you do need to show the charges there in this type of bonding, again, to indicate that there is no sharing of electrons is occurring. Any questions on that there? Yeah. So what will happen if we perhaps maybe put together a couple of these things that we've seen? So let's say we were going to put together calcium and fluorine in this case. So if we put together calcium and fluorine in this particular case, what's going to happen is the same thing. We have our calcium, which is a metal. We have our fluorine, which is a nonmetal, which again should give us an ionic compound. And in this particular case, the calcium is going to give away its electron. And now at this point, can that fluorine take any more electrons? It cannot, right? It is full. And that creates a problem that allows fluorine, right, to be okay, because now it's got to noble gas configuration. Problem, though, is calcium now is a little short there. It's only going to drop back to potassium, which is, again, not a noble gas. So in this particular situation, to accommodate calcium's 2 electrons, we need actually not 1 fluorine to help us out, but we actually will need a second fluorine to basically take on the extra electron there. And in this particular case, that now gives this calcium somewhere to throw its second electron. And the result of that is we will end up with a calcium, which once again now was able to get rid of both of its electrons and become a +2 charge. And we will have our first fluorine that basically picked up 1 electron. And became negatively charged. And we will have a second fluorine that also picked up 1 electron. And also will become negatively charged. And again, they're all not sharing any electrons here. Is that attraction between the +2 and the -1s in each of those that put all that together. And again, sometimes people draw it on the other side of the calcium, the other fluorine, but again, that is what's going on there. So when we look at this, what has happened in terms of our electron configuration, Again, the calcium here was able to get rid of both of those electrons, one to each of the fluorines. So that does allow this calcium here to reach the argon configuration, which is what it is looking to do in terms of its electrons. Now, each of those fluorines basically picked up one electron, and they both have a spot for that one electron in the p subshell there. And that is where they basically deposited that. That allows this fluorine here, again, to end up with basically 10 electrons, which allows it to get to neon's configuration. Same thing here, that guy will pick up one electron, which will allow it to get to neon's configuration as well. So in this case, all three of those guys will end up at the same as the noble gas configuration by accepting electrons and losing electrons, and it creates this really sort of stable situation. That is why when we write formulas for ionic compounds and they tell you to always balance out the charge to zero, maybe you remember that, and we'll talk about when we talk about naming again. Anything that's positive, negative charges, when you put it together to write the formula, you should always equal zero. So that is why when we look at calcium that has a +2 charge and fluoride that has a -1 charge, when we put them together, we need two of those to get the proper formula of CaF2. And that is the simplest way to get to zero. And really the reason why you do that when you write the formulas for ionic compounds to get it to zero is when you do that, that allows everybody basically to reach noble gas configuration. So that is really the reason why we balance out the positive and negative charges to zero when we write formulas, allows everybody to get to that noble gas configuration. Any questions on Lewis symbols for ionic compounds here? So the importance of ionic compounds, obviously, metals, nonmetals, no sharing of electrons, a complete transfer of electrons from one to the next, resulting in ions being formed. And again, you should obviously display it in pictures with the charges involved as well. So let's talk about the other type of sort of bond, which we focus in a lot on in most of the time that we do it. And those are covalent bonds. And once again, here in a covalent bond, this is going to be two nonmetals. And again, the major difference here is we're going to have the sharing of electrons that are happening. So in these covalent bonds, definitely sharing of electrons. And as we'll talk about here again in this chapter, either it will be equal sharing or it will be unequal sharing, but there is some aspect of sharing that's happening. And again, it really is the reason we have nonmetals and nonmetals together. So again, they both really have that urge to keep their electrons and really want to gain electrons. So the best that they can sort of, again, compromise on is, all right, we'll kind of share electrons. And again, sometimes the sharing, they're okay, we'll share equally with each other. Or they'll go, no, we're not going to share equally. I'm going to kind of take more of the electrons than you. But there is some aspect of sharing that happens. So Gilbert Lewis describes sort of the role of bonding as sort of the sharing of electrons, and got all messed up here, so I'll just redraw that there. So if we take something like two hydrogen atoms here together, and hydrogen obviously has one valence electron. When these guys come together, clearly in this case, they are the same element, so they have the identical sort of periodic trends. They're going to basically share these electrons. So what happens is we end up with a bond between those two, and those electrons being shared basically between the two hydrogens. Now, when we count up the hydrogens here, the two hydrogens in the middle does count for the guy on the left, and they would also count for the hydrogen there on the right-hand side as well. There is an attraction, obviously, between those electrons in this shared bonding pair and the nucleuses to each of those atoms on each side. And it is that attractive force between them that kind of locks the electrons into place. So they're kind of attracted to the nucleus on the left there, attracted to the nucleus on the right. So it sort of locks them into place as they get shared between those two. This is basically a covalent bond. It is that sharing of electrons. In this case, you could also represent that, bless you, as a line to indicate the sharing of electrons, which is what should be down there somewhere. And one line represents basically two dots. So as we'll talk about, one line represents two dots, which is a single bond. And as we'll see later on as well, we'll just preview, I guess, the two lines represent 4 electrons or 2 pairs, and that's a double bond. And you could also have represent bonding through 3 lines, which is a triple bond, which represents 6 electrons or 3 pairs of electrons, which is a triple bond. Now, how does this help each of these guys? So in this particular case, when we look at the hydrogen, it basically is sharing 2 electrons. So this guy on the left has basically 2 electrons. The guy on the right also gets to count those for himself. Means that he also gets the 2 electrons. And as we talked about a second ago, hydrogen, if you look on the periodic table, the next element after hydrogen is our good friend helium. And that means hydrogen just needs to get to helium to be happy. And with 2 electrons, it allows it to reach that noble gas configuration. So let me emphasize it here. And as we go through other things, pretty much that's what hydrogen should look like, something like that. It should always be on the outside of a molecule because it can never be on the inside. Otherwise, it has too many bonds. You should never like put dots around hydrogen. You should never put dots and triple bond it as well. Yes, don't do any of those things unless you like a big X. So don't do that. People go crazy with hydrogen, just keep like adding lines and dots and stuff like that. So pretty much hydrogen should always be on the outside because of that. It should never have more than 2 electrons. And pretty much one line to it. If you use lines, there are basically 2 dots to it as to represent the bond. Any questions on that there? So as I mentioned, in a covalent bond, the electrons are shared, and there is that attractive force between the 2 nucleuses, which again really holds that together and kind of keeps those electrons from kind of moving away from each other. So if we look at something like fluorine here, we have F2, and that obviously is 2 nonmetals. So once again, when I see that, I know this is going to be covalent bonding, which means we have some type of sharing of electrons that are going to occur here. And when we look at fluorine, which is group 7, it should have 7 valence electrons. And we have 2 of them here. And again, in this case, because they are identical to each other, we will get those 2 electrons basically to come together and be shared. The result of that there is we will end up with a fluorine here that has a bond. And when we look at this, we can see that these electrons in the middle count for the fluorine on the left, which means he ends up with 8 electrons. We could also count those 2 fluorines for the guy on the right, which means it ends up with 8 electrons. We could also show this by showing the bonding electrons there that are being shared as a line. So this also can represent obviously that as well. Now, in this particular case, kind of similar to what happens in ionic compounds, other than the fact that there's no transfer of electrons, in this case, by sharing electrons, each of those guys within that bond have now been able to hit the magic number of 8, which allows them both to basically end up as the same electron configuration as our noble gases. Any questions on that there? Now, when we look at this sort of drawing here, there are some different types of electrons that we come across. And if we look at all these electrons here, which are just dots, They are not involved in any type of bonding. And we know that because there's frankly no element written on the other side of those electrons there. And these are what are referred to as, in most books nowadays, they're referred to as non-bonding electrons. If you're older like me, they used to call them lone pairs a lot. So if somebody says lone pairs and non-bonding electrons, they basically mean the same thing. They're the electrons that are not involved in bonding. I personally will probably say lone pairs a lot of times. So if I say lone pairs, basically the same thing as non-bonding electrons. And then obviously the electrons that are in the middle there, which as we just talked about, that are being shared, these electrons here, they also have a very creative name since they are being shared within a bond. Those are what are referred to as bonding electrons. So bonding electrons, much like the name implies, are the guys that are obviously involved in bond formation. Non-bonding electrons or lone pairs are ones that are not involved in bonding, but are still there. They're valence electrons that are not involved in those bonding. Whenever you draw Lewis structures, you should always include both of those things. You should always include non-bonding electrons and the bonding electrons, obviously, in the picture. And usually, pretty much in most chemistry classes, we show the non-bonding electrons as dots, and that's how you should show them as well. Sometimes in organic chemistry, they'll use lines to represent them, but we use dots here, and that's what you should use for those non-bonding electrons. Questions on that there? Oops. So a Lewis structure, as we've been seeing, again, can represent both ionic bonding and covalent bonding. Again, the difference also with our covalent bonding is no charges because there are no ions that are involved here. So we do show those lines and sort of the electrons being understood that they're being shared in a covalent bond versus an ionic bond. Again, only the valence electrons are showed in those Lewis structures. They obviously still have those core electrons. But as we talked about when we talked about periodic trends, because they are closer to nucleus, they're held tighter. They pretty much do not participate in any type of bond formation. And we saw that a lot with the ionization energy. As we jumped into those core electrons, when you saw the numbers in terms of the energy, there's a tremendous jump that happens. And that's why they really don't get involved or get sort of pulled off or anything like that. It's just those outermost electrons, which are not held as tightly. So if we look at something here like water, which is H2O, it also is able to fill sort of the octet rule here for everybody. Again, by sharing electrons. In this case, we have our hydrogen and our oxygens on both sides. And in this particular case, it is the oxygen that has to share electrons with both of the hydrogens. Allows that oxygen there in the middle to pretty much get to 8 electrons. Our hydrogen will need to share with the oxygen on each side, again, to allow it to get to 2 electrons each, which is exactly what our hydrogen again needs. And again, we saw that with our fluorine. In the case of fluorine, it allows each of those guys to get to 8 electrons. As you see, those 2 numbers are really important in terms of bonding, 8 and 2. And really pretty much everybody shoots for 8, which is the octet rule. And that allows, again, everybody to achieve that noble gas configuration. Again, with hydrogen only needing to get to 2, which is what is referred to sometimes as the duet rule. That allows hydrogen really just to get to helium, which is all it needs to go. So the idea, and especially in covalent bonding, is atoms will pretty much continue to make bonds until they pretty much hit that octet rule. There are some exceptions to the octet rule, but for the most part, everybody's going to be shooting for those 8, and they will continue to basically make bonds, which means they will continue to share electrons. So atoms will continue to share the appropriate number of electrons needed for basically everybody to sort of get to that octet rule. In some cases, as we'll talk about, it requires just a single bond to do that. Some cases it may require a double bond or a triple bond to allow everybody basically to reach those 8 electrons and that hit that octet rule. So let's talk about that here a little bit more. So again, a single bond represented by one line are 2 pairs, or a pair of electrons, not right, 2 electrons, 2 electrons, 1 pair of electrons, a single bond, again, represented by those. And again, in some cases, that's pretty much all you need to reach that octet rule and get everybody to be happy. And I will say this, when you do draw Lewis structures for covalent compounds, sometimes people like to double bond and triple bond right out of the box because it looks more chemistry like. And you really shouldn't do that, as we'll talk about. Really, you should kind of save double bonds and triple bonds to fix a situation where maybe the octet rule is not met, and not necessarily double bond or triple bond. So a lot of times, sometimes the best sort of structure in a lot of cases, not in all cases, but in a lot of cases, or just a result of sort of single bonding happening rather than double bonding or triple bonding. Sometimes, again, you do have to go to a double bond to achieve that sort of octet rule. And in the case of CO2 here, it actually needs to double bond on both sides here with 2 different oxygens. And obviously a double bond, as we talked about, 2 lines represents 4 electrons or 2 pairs of electrons. And again, by double bonding, in the case here on both sides with each of those oxygens, it allows that carbon there to hit its 8 electrons. Obviously, the double bond also benefits the oxygen as well. It keeps it at 8 on both sides as well here. So that allows everybody to reach the noble gas configuration that they are trying to do. Again, if you leave one as a single bond, not going to allow somebody to reach that electron configuration that is necessary. So in that case, it will then try to form another bond to sort of resolve that situation. And then obviously, in some cases, you do need to kind of go to a triple bond to sort of satisfy the octet rule. And that occurs, for example, in nitrogen here. Nitrogen actually needs to make a triple bond, which is 3 lines. And again, the sharing of 3 pairs of electron or 6 total electrons is a triple bond. And that allows it to get to 8 electrons, as we can see in each case. Here, this is ethine, which is a triple bonded carbon, and that allows each of those carbons to reach 8 electrons. It also needs each of those carbons to share some electrons there with the hydrogens. Allows each of the hydrogens to reach 2 electrons. And again, all 4 of those things have now basically hit that noble gas configuration and makes a really stable situation. So again, we'll talk about sort of the process of drawing these guys, but just keep in the back of your mind there that you really should not, try to double bond or triple bond everything right out of the box. Try to save those to fix sort of situations. So when we're talking about sharing electrons, which is obviously what occurs in covalent bonding, how do we know, whether or not sort of the electrons are going to be shared equally or unequally? And the major thing that we look at when we look at sort of bond formation and covalent bond formation is electronegativity. So we did talk about electronegativity in the previous chapter. We're going to use it a little bit more in detail here in this chapter. But as we talked about last time, electronegativity is really that ability, right, of an atom to bring electrons towards itself. And in general, the trend increases as you go up and to the right and decreases as you go down and to the left there on the periodic table. So it really is sort of the overwhelming thing that you look at when you're basically looking between two atoms and whether or not those electrons will be shared equally or unequally. That is what is sometimes referred to as bond polarity. When you kind of look at just the bond between these two atoms, how are they going to share those electrons, is what is referred to sometimes as bond polarity. And electronegativity is really the main thing that we look at. And it does help us sort of distinguish between sort of different types of covalent bonds. So for example, if we took something that we saw earlier, which is our hydrogen and our hydrogen here, when they are sharing these electrons, because they're really both hydrogens, they both pretty much have the identical electronegativity and all identical sort of periodic properties. And that means that both of those hydrogens are going to pull on those electrons that are being shared equally, are being shared between them. And we're going to end up with really an equal sharing of electrons. So you can kind of think of it like a tug of war, like two people pulling on a rope. So if you have like two people pulling on a rope with a flag in the middle and they're pulling equally, the flag is just going to kind of stay in the middle, right? It's not going to go anywhere. So everything's going to be shared really equally. And also when we look at our friend, the fluorine guy there that we saw earlier, they're both obviously fluorines as well. And the result of that is we would expect those electrons to be shared equally as well. And in a situation where we have electrons being shared equally between the bond or between the two atoms, that is what is referred to as a nonpolar covalent bond. Or most people just call it a nonpolar bond. I'll leave the covalent part out of it, but it is a covalent bond sharing of electrons. So when we do have that situation that occurs, we do end up getting equal sharing of electrons. And again, that is what is referred to as a nonpolar covalent bond. Now, what happens if we sort of mix it up and put one of those guys together with the other? So if we look at something like HF, and it looks something like this. When these two guys get together, we now have two different elements and they have two different sort of periodic sort of properties, especially with electronegativity, right? We talked about, I think last time, the most electronegative element you can have is fluorine, right? Upper right of the periodic table is as far right as you could go other than noble gases. And when fluorine and hydrogen get together, it is actually going to be the fluorine that is going to go, I would like the electrons more than you, basically. So what ends up happening when these two guys get together is we end up with fluorine saying, if my kind of lines are the electrons, going to kind of jump and take all those electrons closer to itself. And a little bit of it will kind of stay, kind of closer to the hydrogen side. The result of this happening is we're going to get actually an unequal distribution of those electrons between the two atoms. And what we will end up with is the fluorine side will have really more electrons sort of hanging out near it. That will make the fluorine side more positive or more negative. Should make it more negative as electrons are negatively charged. And what happens is the fluorine side here will gain a partial negative charge. That's a delta negative sign. And because the hydrogens have the electrons sort of moving away from them, it will create itself a sort of partially positive charge as the electrons sort of migrate away from them. And it creates a partial positive charge. You could also represent this through what is sometimes referred to as a dipole arrow. And when you draw dipole arrows, they look like this. And it always points to the more negative side of the bond or the molecule. And the back part, which kind of makes like a plus sign, is to the more positive side of the bond or the molecule. So a lot of times that is represented just like that with our dipole arrow. Why is it only a partially positive and partially negative charge, and not like a full positive charge and a full negative charge that occurs in this case. They are sharing. So there is still some aspect of sharing that's happening here. So it isn't only going to make a partially positive and partially negative because they're kind of hedging their area where they're at kind of a little bit more one side versus the next. They have not fully transferred, which is what we have occurring in an ionic compound. The electrons fully transfer from the metal to the non-metal. So the metal becomes fully positively charged. The non-metal becomes fully negatively charged. Here it develops a partial sort of charge because of that unequal sharing of electrons. So there is still that sharing of electrons that are happening. There is no transfer of electrons. It may get close, but they're still hanging on, which creates these partially positive charges and partially negative charges rather than full positive charges and full negative charges. So what I drew here is what is referred to as a super zoom polar covalent bond, are really just referred to by most people as a polar bond. So a polar bond results from the bonding that occurs between two nonmetals, and the result of the having different electronegativity values and sharing those electrons, unequal sharing. But again, there's still some sharing of electron that occurs. In a nonpolar bond, we have pretty much equal sharing of electrons. And you could think of a nonpolar bond, I guess, as sort of like a neutral bond, if you will. There's really no positive side, no negative side in a nonpolar bond, but there definitely is sort of a positive side and negative side in a polar bond. And in later chapters, as we'll talk about, it's a really important whether or not those type of bonds are present, say, in a compound, as it affects things of how they interact with one another, how one molecule can kind of interact with another molecule. Most molecules, as we'll talk about in later chapters, interact through what are referred to as intermolecular forces. And those are really basic interactions of positive and negative sides of things being attracted to each other. So obviously things that are polar are attracted to other things that are polar because they get attracted to one another from the positives and negative side of one another. Things that are nonpolar and polar really don't mix, kind of like the layering we saw yesterday in lab when we poured the hexane, which is nonpolar, and the water sort of aqueous part, which is polar. They separated out from each other because they have no way to interact well with one another. So that creates a lot of problems when nonpolar and polar things try to get together. So there's the smear, there's the thing. So we do draw these arrows a lot, and this should not be confused in terms of different types of polarity that we'll talk about. So in the next chapter, we'll talk about a lot more. And in the next chapter, we'll talk about what is referred to as molecular polarity. And molecular polarity is about whether or not the entire molecule as a whole, with all the bonds that are present, is polar or nonpolar. Is there overall equal sharing overall the entire molecule? And that's not to be confused with really what is sometimes referred to as bond polarity, which is the polarity just between these two atoms. You know, are they going to share the electrons equally or non-equally? What sometimes confuses people is we do use this arrow for both. We do use it to represent molecular polarity, and we also use it to represent bond polarity. So sometimes that confuses people. So, and what also can confuse people as well is, as we will see in the case of diatomic molecules, they actually are the same thing because there's only one bond in the entire molecule. But when we get to things that have multiple bonds in there, you have to take other things into consideration for molecular polarity. So when we talk about our sort of three different types of bonding that sort of occur, we could kind of think of it as one sort of extreme to the other. On one extreme, we sort of have an ionic bond, which is between a metal and a non-metal. And we always get the electrons to be transferred here. And that results, as we talked about, with our positive cation and our negative anion being formed. And is that electrostatic attraction, no sharing of electrons here. And that is something like, say, sodium chloride, metal, non-metal, going to be basically holding that together. On really sort of the other end of the spectrum, we have really a nonpolar covalent bond. and that is between two nonmetals. That is equal sharing of electrons. And a couple of examples that we've seen so far, like H2 or F2, nice equal sort of sharing of electrons. And you could kind of think of in the middle of those two is the polar covalent bond or the polar bond, which is also two nonmetals. It is also, as we talked about, sharing of electrons, but it's unequal sharing. And an example obviously would be this guy, and that results in obviously that partially positive charge, partially negative charge. So at one end, we have the complete, you take my electrons and accept them. And on the other end, we have, no, we're just going to kind of share equally with each other. And kind of in the middle is, well, I don't want to share equally with you. I'm going to kind of pull the electrons more, but not to an extent where they actually transfer. So they're still hanging on. And as we will see in the case of something like HF, they are barely hanging on, but they are still hanging on. And it's there are some degrees, I guess, of bond polarity, some almost equal sharing, and some to the point of almost transferring of electrons that can kind of occur. Any questions on the different types of bonding here? All right, so let's take a look a little bit more as to how we determine in terms of, is a bond going to be polar, non-polar? And as I mentioned earlier, it really is that electronegativity, which is the biggest sort of factor that you look at to help you try to decide whether or not we will share those electrons equally, unequally. You could, in a sense, even use it to determine if it's going to be ionic, but as we'll talk about, you really don't need electronegativity values to help you determine that. You pretty much just need the fact of that's a metal and a non-metal, pretty much right, ionic, and you should be in good shape. You really don't have to figure much out in terms of that. So looking at electronegativity, as we talked about, the ability of an atom basically to bring electrons towards itself. And again, the general trend, as we talked about, up and to the right, going to increase electronegativity on the periodic table, with fluorine being the most electronegative, and obviously going the opposite way, left and down, going to decrease in electronegativity. Electronegativity is related to electron affinity, which is that energy change when they gain electrons, and ionization energy. And something like fluorine has a high electron affinity, which means it likes to gain electrons, and it has a high ionization energy, which means it does not like to give away its electrons. And that means that it will have a high electronegativity, which means it likes its electrons and it likes to gain electrons. It likes to attract electrons. Sodium on the other side, which is obviously all the way to the other side of the periodic table, has pretty much the opposite there. It has a low electron affinity, which means it's not really all that interested in sort of gaining electrons. And it has a low ionization energy, which means it's not all that interested in hanging on to its electrons. It's willing to give them away. So it does have a low electronegativity. Now, a guy by the name of Pauling came up with a method of calculating electronegativity. And basically Pauling's method or calculation runs from 0 to like 4. And 4 is the most electronegative. So something with a value of 4, like fluorine, is very, very electronegative. And somebody closer to 0, not so much. So not so much there, not very electronegative in that case. And we could really use the differences in electronegativity values to help us understand whether or not, when we put together two elements, would we expect those electrons to be shared equally, which would be a nonpolar bond, unequally, which would be a polar bond, or would we expect them to sort of transfer from one to the next, which would be an ionic bond. So a lot of times what we calculate using Pauling's method is what is sometimes referred to as delta En, and that is delta sign is the change in electronegativity values. And basically you look up on the table, you find the two electronegativity values for those elements, and you basically subtract them. You subtract them in a way that gives you a positive number. So you basically just take the difference. And if you do that, and typically speaking, you get somewhere between 0 and 0.4, that is usually considered a nonpolar bond, which means essentially it's going to be equal sharing of electrons. It will sort of be neutral in a sense. There will not be a positive side or a negative side to that particular bond. If you get a difference in electronegativity value above 0.4, which is like 0.5, to below 2, typically, that is going to usually result in some type of polar bond. And that would mean that those atoms we would expect to share the electrons unequally. So there would create a side that's more positive, a side that's more negative. And typically speaking, above 2 is usually ionic, which means there would be no sharing of electrons. There would be a transfer of electrons. Now, there should be a little asterisk here. And the asterisk is it doesn't work well for all ionic bonds. So there are some ionic bonds where the difference is less than 2, but it's still ionic. So really, as I mentioned before, you pretty much don't need the difference in electronegativity value. Once again, if you see you have a metal and a non-metal, you should just roll with ionic and you'll be in good shape on those. So really, a lot of times we do use electronegativity values to help us out with sort of covalent bonding. And again, it's not necessarily needed per se for ionic bonds, as it should be a metal and a non-metal. Any questions on that there? So if we look at electronegativity, which is that trend that we just talked about there. So if we look at a chart of electronegativity values here, as you can see, and we could use it for some of the stuff that we saw before. So we had sodium chloride, right? And we had HF, and we'll do F2. So if we were to sort of use this chart and to calculate whether or not something is going to be ionic, covalent, polar, or non-polar, if we started with our sodium, for example, if we look up sodium there on the chart, it is 0.9 is the value. Our chlorine there is something, let's see where are you at there, 3. So if we take the difference in electronegativity here, that's going to be 3 minus 0.9. That's a lot of math. I'm going to go with 2.1. And 2.1 is above 2. And here we would know that it is ionic in this case, right? So we should get that transfer of electrons that occurs. If we look at fluorine here, fluorine is 4. And this fluorine would be 4. So the difference in electronegativity values here would be 4 minus 4. That is 0. And that is definitely going to fall in the 0 to 0.4 category. And that is going to be nonpolar bond. Now, actually, when you do get a electronegativity difference of 0, it is also sometimes referred to as a pure covalent bond. And pure covalent bond is a fancy way of saying like perfect equal sharing of electrons. It is still nonpolar, and it's a nonpolar bond, but sometimes books and stuff will refer to it as being pure covalent, which pretty much means nonpolar and nice perfect equal sharing. As we saw on that chart, right, our chart ran from 0 to 0.4. So if somebody has like a 0.4 difference or a 0.3 difference, it is considered nonpolar. It is considered equal sharing of electrons, but really it's not perfectly equal, right? Because there is a difference, right, in terms of the number. It is slightly hedging one way or the other, but not enough to be considered polar. So there is that sort of wiggle room between that. So when you do hit something that is 0, that's like we got perfect, nice equal sharing of electrons between those two. Now, if we look at something like HF, hydrogen here is 2.1. Fluorine is 4. So if we do our difference in electronegativity, it's going to be 4 minus 2.1. That's like a 1.9 in that case. 1.9 is like almost that limit of ionic, but it is still going to be polar, right? So that is pretty much unequal sharing of electrons that you have between those. And again, that's because fluorine obviously is very electronegative. Any questions on that there? All right, why don't you try some here? Why don't you do, let's do the carbon hydrogen bond. Let's do potassium and chlorine. Let's do nitrogen and oxygen. Let's do sulfur and oxygen. Let's do carbon and sulfur. All right, using the electronegativity values that you see there, are they polar, nonpolar, or ionic? Take a few minutes, see what you come up with. Okay, let's take a look here. We'll start with the carbon hydrogen. So carbon is 2.5, hydrogen is 2.1. So when we do our difference here, it's going to be 2.5 minus 2.1. That's going to give us a 0.4 difference. That would make it polar, nonpolar, ionic. Should be nonpolar. That's really the reason why it goes up to 0.4, because pretty much most organic compounds are carbons and hydrogens, and they're nonpolar. So that's sort of the cutoff there. In reality, even though it's being shared equally, right, the carbon is pulling a little bit more, right, than the hydrogen, but not to the extent that it'd be considered polar in this case. We look at potassium and chlorine here. Potassium is 0.8 and our chlorine is 3. So we take the difference there, 3 minus 0.8 looks like a 2.2, I think, and that should be ionic. Again, really didn't need the numbers there because that is a metal and a non-metal, so we should know it's ionic. For example, though, if you took something like, I don't know, like maybe cesium and iodine, it will get less than 2. So there are possibilities where you can connect a metal and non-metal and have less than 2. So just knowing that it is a metal and non-metal and it's ionic is pretty much all you should need. We look at nitrogen, oxygen. Nitrogen being 3, oxygen being 3.5, so that's going to give us 3.5 minus 3 for our difference in electronegativity, and that's going to give us a 0.5. That is above 0.4, which means that this should be a polar bond in this particular case. Looking at sulfur and oxygen, so we have our sulfur and our oxygen. Sulfur there is 2.5. Oxygen is 3.5. So when we take our difference in electronegativity, 3.5 minus 2.5 going to give us a 1, which is definitely above 0.4, but below 2. So that is going to be a polar bond as well. Any questions on that so far? Which one? The carbon and sulfur, I think is the last one we need. Carbon and sulfur, and in this particular case carbon going to be 2.5, sulfur going to be 2.5 as well, I believe, and that means that our difference in electronegativity going to be 2.5 minus 2.5, I think that's 0, and that is going to be a non-polar bond. Yeah. If there's any questions on that one there. This is a good demonstration that you can have actually 2 different elements that can share the electrons equally because they have the same electronegativity values. And that is because when you look at the periodic table, there is what is sometimes referred to as a diagonal sort of relationship. We look at carbon, which is here, and we look at sulfur, which is here. They are diagonal of each other. One is further up, but one is further to the right. So they kind of cancel out their differences and they end up with the same electronegativity values. You also see that there, say nitrogen and chlorine, right? Those guys are also diagonal of each other, and there are a few others that are on there. And it's usually diagonal kind of down and over. One is usually that diagonal part that sort of cancels each other out that way. So it is possible to have two different elements that will share the electrons equally. Definitely, if you have two of the same elements, they're going to share it equally, but you can also come across sometimes when they are different and will share it equally. Question on that there. Now, in terms of our polar guys, right, if we were to draw our bond dipoles for these guys, the arrow should head towards the oxygen in this case, right, as it is more electronegative. And that means that the oxygen in that bond would be more partially negative versus the sulfur, which would be more partially positive. Same thing here, it would actually head towards the oxygen as well. And the same result there, our oxygen would be more partially negative. Our nitrogen would be more partially positive in this case. You would not draw any for the nonpolar guys, right? Because they are sharing electrons equally, so no bond dipole arrows. First off, any questions on how to use table or calculate it? Obviously, the values would be provided to you if you needed them, but you should still know the general trend in electronegativity values. All right. Now, do you always need to sort of calculate the difference in electronegativity values to help yourself make those determinations? The answer is not in some cases. And in some cases, you really don't need necessarily the values. You can use just the general trend in electronegativity to help you make a pretty educated guess. So for example, if we took something like nitrogen and oxygen, they are in the same row. And we see that oxygen is further to the right, which means it should be more electronegative and it should result in a polar bond. So even without the numbers, just knowing that they're in the same row and one is further to the right than the other should result usually in a polar bond. Also, if you look at the sulfur and the oxygen, they are in the same row, or not row, they're in the same group or column. And here we do see that the sulfur is lower in the group than the oxygen. So oxygen is higher up in the group, which means it should be more electronegative than the sulfur, and it should result in a polar bond. So if you're trying to determine two things that are in the same row on the periodic table, are the same group, you could just use a general trend in electronegativity. And if they're pretty much in those things, they probably will be polar because they'll be away from each other and there will be that difference. You don't really need the numbers. And obviously, if something's ionic, that's a metal and a non-metal, once again, you really don't need the numbers for that as well. So in a lot of cases, you can make a fairly good guess as to whether or not it should be polar or non-polar just based on their location on the periodic table. Again, as long as they maybe are not sort of diagonal of each other like we were talking about, you know, you'll probably make a pretty good guess. Any questions on that there? There's that. So here's just a breakdown of what we were just talking about. Again, our 0.1, basically 0 to 0.1. 0.4 is a nonpolar bond. Again, this is what I was talking about earlier. Some books will go, if it's perfectly 0, it is a pure covalent bond, but it's still really also considered a nonpolar bond. So you could just call it a nonpolar bond if you want, but sometimes people will use that sort of terminology for something with a 0. Again, pretty much 0.5 to less than 2 is going to be our polar, and in most cases, it's going to be above 2 is going to be ionic. Now, we also sometimes will talk about, and not too much these days, but sometimes people will talk about bonds in terms of percent ionic character. And it kind of follows the same sort of scale as you can see here. If you have 100% ionic character, that means that you will have electrons being transferred. You have an ionic bond that's basically happening. You'll have a really big electronegativity difference, which means that those electrons will basically shoot over. On the other end of the extreme, basically, if you have 0% ionic 0% ionic character, you pretty much have a pure covalent or non-polar type of bond that's happening. Again, people don't use it too much these days, but sometimes it does pop up. So as we've seen, atoms with very different, big differences in their electronegativities, definitely when we put something from the left-hand side together with the right-hand side, that's usually very conducive to an ionic bond being formed, electrons being transferred. Things that are pretty much kind of piled there into the same spot on the periodic table will tend to have those very similar sort of electronegativity values. And that's more suited to some type of sharing of electrons that occurs, either nonpolar equal sharing or polar unequal sharing of those electrons. And that's how we know that's generally what occurs. So that is what we just talked about there, our percent ionic character. And again, as I mentioned, I would go more with the metal non-metal for our ionic versus using the numbers, because you will in some combinations get some that are less than 2, but they're still ionic. Any questions about bond polarity and bonding in general here so far? So last thing on this is, again, what we are talking about here specifically with the electronegativity values is specifically bond polarity, just determining between these two guys, you know, are they going to be shared equally or unequally? And the one place only where that sort of crosses over is when you have something like we saw earlier, say these two things. We know from our conversation there, right, that that's going to be a nonpolar bond. We also know from what we just looked at that these guys here are going to be a polar bond. And that is the bond polarity for both of those guys. But when we look at each of these things, these are both diatomic molecules. Which essentially means they only have 2 atoms involved, and they have how many total bonds in each of those things? Just 1, right? So in that case, because the guy on the right, the F2, has only 1 bond, and that bond is nonpolar, that molecule would be nonpolar overall. And that would be the molecular polarity of it. On the left-hand side there, the HF has only 1 bond, and that 1 bond in that molecule is polar. And that would make HF also a polar molecule because that. So the only place really where bond polarity and molecular polarity are really the same is when you're dealing with a diatomic molecule. And that is because, frankly, there's just 1 bond. So if that bond is nonpolar, the molecule will be nonpolar as well. And if that 1 bond is polar, the molecule will be polar as well. When you get 2 or more atoms, as we'll talk about in the next chapter, there's a lot more you got to kind of take into consideration. But definitely in a very simple molecule, diatomic molecule, both the bond polarity and the molecular polarity will be the same. Any questions on that there? All right, we will lay it up there for today.